Okay, so today we're going to do a review of Chapter 3. I messed up when I was first filming this, that's why there's already text on here, so I'm just going to walk through this real quick. So Chapter 3 is dynamic response, and what I'm doing is I'm going through the summary page at the back, and I'm going through a couple of things. So the first is review of Laplace transforms. So if you have like equations of motion like this, x double dot, 3x dot plus 4x, and you assume the initial conditions are 0, you can just go straight to this and you get big X, S squared, 2 dots makes 2 S's, 1 dot makes 1 S, no dots just makes lowercase x to capital X. Really what you're doing is you're going from the time domain to the Laplace domain, and then if you solve for x on the left side and divide, you can get a transfer function g, which is x divided by u, and you get 1 over s squared plus 3s plus 4. And then by the way, if you draw this in block diagram form, you're going to get g and big X like that. And that's sort of your control block diagram. It's open loop, but it's still a control block diagram. If you have initial conditions, you need to use these formulas. So Laplace transform of x dot is s big X minus x naught, and then Laplace of x double dot is s squared x minus sx naught minus x dot naught. So this is the initial position and initial velocity. In this example here, I had no initial conditions, so I didn't need to worry about that. Okay? The next thing that is very useful to find is if, so this is what's called the final value theorem. Well, really, I would say the next thing, by the way, is probably inverse Laplaces, inverse Laplace. And you need to know the common ones, right? So in this case, let's say u is a step, right? So that's a step input. Then that means that x is going to be 1 over s squared plus 3s plus 4. And you need to do partial fractions to inverse Laplace this. And so this is a real root, so you're going to get a over s. And then this is a imaginary root, so you're going to get bs plus c over s squared plus 3s plus 4. Now there are other YouTube videos you can watch, not from me, but on how to solve A, B, and C. I don't think it's relevant except for academic purposes. What really matters is that you can get x of t, which is a plus, you're going to get b e to the negative sigma t cosine omega t plus c e to the negative sigma t sine omega t. And what is sigma and omega? Well, the roots of this quadratic are going to be negative sigma plus or minus omega j. And since this is a quadratic, it's going to be negative 3 halves plus or minus 1 half, 9 minus 4 ac. And that's just the quadratic formula right there. So then sigma is 3 halves, and then omega is this thing. This is going to be an imaginary number. 9 minus 36 is a negative number, so this is going to be some omega. And that is going to be your system there. So if you wanted to plot this, right, t and x, your initial condition was 0, you hit it with a step. Because this oscillates, you know this oscillates, but the system is stable because the real component is in the left half plane, this is going to shoot up and oscillate, and it's going to level out at A. Now A has a special name, it's called x steady state. It is the steady state value of x. And that is what they're showing in here for the third concept, which is what is the final value or x steady state. And the way you can do that, the way you can find x steady state is by looking at your transfer function and plugging in s equals 0. And what you get is 1/4. Okay? This only works if u is a step input. If you hit it with an impulse, it's just going to come back to 0 because it's stable. If you hit it with a ramp, it's going to go off to infinity because you're hitting it with a ramp. But if you hit it with a step, it's going to settle out to a final value, and that steady state value is using this formula. Plug in s equals 0, you get 1/4. So this is 1/4, which means A is 1/4. Okay, and you can verify this in simulation if you need to. Okay, there are a couple more things in chapter 3. All right, we're back, part 2. Chapter 3, dynamic response review. So the other thing that matters is how do you get or how do you analyze a block diagram that looks like this? Okay, this is G, the plant. G is equal to Y over U, right? I know that that's a fact. This is my plant dynamics. This is going to be called H. This is my sensor dynamics. Sensor. This is going to be my controller, my control dynamics. And I'm going to call this capital F. It's like a command generation block. But basically, and then I have a feedback loop here, so this is a summer. This is what I call G open loop, GOL, GOL. If you watch some of my Python videos on control system dynamics, you'll see that I usually have GOL, GOL as like my my variable name. It's because it's open loop. This is my open loop system, open loop. What I want to know is my closed loop system, which is Y divided by R, where R is the reference command. U is the control input, like force. R is the reference command. It's something that I'm trying to track, okay? And so how do you close the loop? So chapter 3 is all about closing this loop. So if I drew a control block diagram, basically what I want is I want R and I want GCL and Y. Because if I have one block, I can analyze one block. And so let's get all of my blocks down to one, okay? So the first thing that you need to do is do what's called cascade, okay? And you need to take the two blocks that are right next to each other and just multiply them together. C, G. Okay, now they're just multiplied together. And then you do what's called the feedback rule, which is closing this feedback, and it's saying that this entire block here, right, is going to be CG, which is whatever's in the top. Whatever's in the top goes in the numerator, and then 1 plus CG, whatever's in the numerator, times H, the denominator, okay? And so if I close that loop, I'm going to get this. This is going to be F over here, this is going to be R, and this is going to be Y. And so this is called the feedback rule, feedback rule. And then finally, you just cascade the last two blocks. And so if I look at this, I have FCG over 1 plus CG, H, R, and Y, okay? And so if I gave you if these are letters obviously, but they represent transfer functions, so if I gave you transfer functions, you can combine them all into one using this formula here. If this is just a line and there's no block there, then H would just be 1, and you would just replace H with 1, but CG times 1 is just itself, and so it kind of just shakes out that way. Okay? There's one more. This video is kind of short, so I'm going to go ahead and I'm going to take a picture of this real quick. There's only one more thing that I need to talk about for chapter 3, and I don't want to make too many videos. I'm going to scan the board. Okay, and then upload that to the Google Drive folder. If you're paying for this class, then you get that privilege. Okay, so the last thing in chapter 3 is analyzing first and second order systems, okay? So if I take the, shoot, I forgot that. I'm gonna assume it's number 4. It's probably number 5. This is item number 5 of chapter 3. It's analyzing first order systems. And so if I take a general first order system, A over S plus A, I have one pole at negative A, it's stable. The response to a step looks like this. And I know it goes to 1 because the final value theorem says that A over A is 1. But what matters here is what's called the time constant, and that is here. And so at right here at, I think, tau, which is equal to 1 divided by A, is 63% of the final value. So if you look at the time response of the system, you can get that there. I think there's also a settling time or a rise time. It looks like they just have a time constant. So 63% is 1 over A, and that's it. Okay? So that's basically all you need to know for analyzing first order systems. That's pretty simple. Okay? For second order systems, there's a couple more things that you need to be aware of. So I think hopefully it's in the summary. This summary kind of stinks. Okay, so for second order systems, so this is, I guess, review number 6, is analyzing second order systems. And there's a couple things that you need to worry about. First, if you have omega n squared over s squared plus omega n squared, this system oscillates forever, and there's no damping. If you have g equals omega n squared over, let's do sigma squared, s plus sigma squared like that, this is actually critically damped, and does not oscillate. And by the way, this has a damping ratio equal to 0, this has a damping ratio equal to 1. If G equals AB over S plus A, S plus B, then this is overdamped, does not oscillate, and the damping ratio is greater than 1. And then the last one, which is what really matters, is omega n squared get s squared, 2 zeta omega n s, omega n squared. And so you have the natural frequency omega n squared, or sorry, omega n is the natural frequency, and zeta is the damping ratio. And in this case, it's underdamped, and zeta is between 1 and 0, and it oscillates. Okay? So my poles for an underdamped system are here and here. This is sigma. This distance here is the natural frequency. And this distance here is the damped natural frequency. The poles, you can find the poles using the quadratic formula, but you basically get the poles are negative sigma plus or minus omega dj, or you can write it as negative zeta omega n plus or minus omega n square root of 1 minus zeta squared j. Those are your poles. The response to a step, just like the first order system, looks like this, where this is A, this is 1. Okay, sorry about that. So I'm trying to remember my train of thought here. So basically, these are your second order systems: no damping, critically damped, overdamped, or underdamped. And if you're underdamped, your poles are here and here, they're complex conjugates. Here are your poles. Your system's going to oscillate. Your rise time is 1.8 divided by omega n. And your rise time is the time it takes to go from 10% to 90%. That is your rise time. Your peak overshoot value is a complicated formula based on damping ratio, and I don't think it's important to write it down because you can just use a computer to calculate it. The settling time, though, is 4.6 divided by zeta omega n, and that is where your system is within 2% of the final value. Okay? And that is basically everything that you need to know for chapter 3.